Very good. Let's get started. Hello, everyone, and welcome to this webinar brought to you by Classiq. My name is Yuval. I'll be your host today. Joining me today are two of my colleagues, Lior. Hi, Lior.
Hello. Hi, Val.
And Amir. Hi, Amir.
Hi, everyone.
Many of us believe that quantum computing will be critical to companies in the finance field. And today we will try to describe some of the issues associated with quantum in finance, as well as potential solutions to these issues. Here's what we're going to do. I will give a very short introduction to Classiq. Amir will present some of the issues in applying quantum computing to finance. And Lior will demonstrate some of the solutions that Classiq offers for these problems. Then we'll do Q&A. How does that sound? Good, I hope. Speaking of Q&A, there's a chat area at the bottom of your screen. Please submit your questions at any time. I will do my best to address them during the webinar, and those that we don't, will respond to them by email after the webinar. So Classiq is a software company. We make a platform for what we call quantum algorithm design. Our software helps design sophisticated quantum algorithms. It does so by converting high-level functional models into quantum circuits. So on the left of the slide, you see a human-readable functional model, and on the right bottom, a quantum circuit that was automatically generated from it. This method avoids the need to build circuits at the gate level. It makes it possible to design both for today's quantum computers, as well as for the larger machines that we'll see in the future. Here's what the workflow looks like. The Classiq software accepts a high-level model, as well as a list of constraints that are important to the designer. More about constraints later. It then outputs the quantum circuit in a variety of formats, Qiskit, Q-sharp, Cirq, and so on, so it can run on pretty much any universal gate-based quantum computer. We'll see a demonstration of this workflow in a bit, and of course, work on most of the cloud providers. And with that, I'd love to turn it over to Amir. Amir, the stage is yours.
Thanks, Yuval. So hopefully everyone is seeing my screen now. My name is Amir Naveh. I'm head of algorithms at Classiq. And I'll talk a bit about the problems, the hard computational problems in finance and how quantum computers can help solve these problems. So in quite a lot of use cases in finance, the bottleneck today is computational power, either accuracy or how long it takes to actually perform these computations. So for complex derivative pricing, risk assessment, portfolio optimization, other hard optimization problems, really classical computers are the bottleneck for getting these very good results. Come quantum computers, which in some of these use cases can help, either speeding up quadratically some of the computations, giving us lots of orders of magnitude of improvements, improved Monte Carlo simulations, or even possibly larger improvements in optimization tasks. So when we come to model a financial problem into a quantum computer, usually we break it down into 3 steps. First is we try to find a quantum representation for the problem of interest, see how it actually models into a quantum computer. Second part is building the circuit, the actual gate sequence that will run on the quantum computer. And finally, obviously execute it on some hardware, quantum hardware, giving us an improved result someday in the future. Obviously today, it's not the case and the quantum machines are not strong enough yet. So maybe let me start with an example of option pricing. So when we're trying to price complex derivatives, the first thing we'd want to do is really find the underlying distributions of the assets involved. So here we see a log normal distribution function, which is a very common distribution of many assets, of stock prices, etc. And when we come to load this into a quantum computer, we'd need to make this probability distribution discrete. And then if we, for example, sample it in 8 points, we can load this into a 3-qubit quantum computer. And of course, when we're talking about a 100-qubit quantum computer or a 1,000 qubit quantum computer, these things become very, very large. And this is some of the power of the quantum computers and also some of the challenge. And this brings us really that when we're talking about useful quantum circuits, when we're talking about actual quantum software that will bring us benefits, we're talking at the very least on a few hundreds or thousands of qubits. And today we're at a few dozens, but hopefully we'll be there in a couple of years. And then we actually go into a very hard design problem. How do we create these circuits? How do we know which exact gates to put when the circuits become much larger? And this problem is actually quite similar to what happens in the classical world. None of us are wiring together the transistors or putting together classical logical gates in order to perform what we're trying to do. Rather than that, we have high-level modeling tools, for example, VHDL or Verilog, where we have a model of what this classical logic is supposed to do, and then it is synthesized both automatically and optimally in ways that are impossible to do manually. And this is exactly what the Classiq platform does. So in a minute, Lior will dive into a demonstration, and you will see this happening live. But what you see here on the left-hand side is a model of the circuit, a description of what the circuit is supposed to do and constraints on the circuit. And on the right-hand side, you see the sequence of actually which gates are performed on which qubits. In this case, it's in the format of OpenQASM, but it could be in Cirq or Q-sharp or any other gate level representation you're comfortable with. The platform supports them all. So just to give a little bit of a background or introduction to the demonstration by Lior, we'll show three things. First would be an introduction use case of the state preparation and how our platform deals with that. We've already talked about that in the log normal distribution slide. Second would be a financial use case called value at risk. Maybe some of you are aware of that. One of the problems in risk assessment or risk analysis, this is something that quantum computers can vastly speed up using a quantum algorithm called amplitude estimation, which speeds up things that are usually done with Monte Carlo simulations. And our platform enables a very flexible method to do these kinds of tasks, whether it's risk analysis or other things that are using this amplitude estimation framework to really describe your financial model within it. And finally, maybe the value at risk here, this is important to show. What we're trying to really find out is what the worst 5% cases will be, right? So that's the financial problem this is coming to solve for those of you that are unfamiliar with this use case. And finally, I will show how to generate complex oracles. Oracles are a very common building block in many of the quantum algorithms, specifically in finance. It is also used in amplitude estimation, and essentially in many search algorithms, what you're trying to do is find or model your specific problem into this oracle. So you need a descriptive language in order to generate this. The oracle is just a complex quantum circuit that really does what you're trying to find out financially. So we'll show how the Classiq platform enables generating much more complex oracles than are available anywhere else today. With that, Yuval, that's all from me for today.
Thank you very much, Amir. And before I turn it to Lior, just want to remind everyone there's a chat button at the bottom of your screen. Feel free to submit questions and we'll try to address them to the best of our abilities. Lior, to you.
Thank you, Yuval. Thank you, Amir, for the introduction. I will share my screen now. I hope everybody can see my screen. So, hi, everyone. My name is Lior. I work at Classiq as a quantum software engineer. And today we're going to get our hands a little bit dirty by solving some financial related problems using quantum algorithms and quantum circuits that will be generated using the Classiq platform. So this is our platform, basically. You can run it using a Python SDK or a VS Code extension. I chose to show you the VS Code extension because I think it will be a little bit less intimidating if you're not familiar with writing code. This is what you see here is a JSON object, and inside this JSON object, we have our model, our high-level model to describe the quantum problem that we want to solve. And this model is built out of constraints. And the first constraint that defines the problem is the number of qubits that we allow the circuit to have. So in this case, we have 4 qubits in our circuit. The second constraint is segments. And segments is the way that we chose to model the quantum problems in our platform. Each segment is built out of function that has a different functionality. And this functionality comes in hand in the function parameters. And in this example, the relevant function parameters, sorry, I didn't mention that. I'm going to show you now the first example, which is the state preparation, as Amir said. And in state preparation, I want to load the distribution onto my quantum circuit. So the first parameter that I want to insert into this two is obviously the probability that I want to load, and this is my desired output. I have two more constraints that are additional to my problem. The one is the depth, and the second one is the error. Obviously, this algorithm is approximated, so I have some kind of error that I need to allow my algorithm to have. And I choose here an output format to be custom, and I run the command line in the VS Code. I press generate quantum circuit. I want to save my result into a folder. I call it hello1, and I press enter. And now there is an engine that wraps all of the constraints and solve the model in order to satisfy all these constraints. And you can see that we got two outputs. The first one on the right is an intermediate representation of the circuit. This is in a custom form. And the second one is the quantum circuit. And you can see that we got a pretty complicated quantum circuit that if I had to allocate all of these gates manually, it would take me a lot of time. And this circuit basically loads the distribution that you saw here onto the quantum circuit. And the next thing I want to show you is that, okay, we're in the NISQ area. So this circuit might be too deep to run on a quantum computer. And obviously, a state preparation is sometimes only the first part in a quantum algorithm. So we can't allow ourselves to have so many gates. So the depth of the circuit will cost me in some kind of an approximation error. So I need to loosen a little bit the error. I change it to 0.05. And let's say that I want my output to be in a Q-sharp format. I press generate again. Let's call it hello2. And now, again, I have two outputs. The first one on the right is the intermediate representation of the circuit in a Q-sharp format. I can call it one. And the second one, you can see that we got a much shallower circuit that can fit the NISQ area. So this was a quick hello world example, so you can get the feeling of how our platform looks like and what you can gain with it. And we can dive into the next example of the more financial related problem. And in this case, I'm going to show you some risk analysis problem. As you can see, this is again the same structure of the file as you saw before of the model. We have this JSON object contains constraints. Again, we have the number of qubits that will define our circuit, and we have the segment and the function. And the only thing that changes between the files is the functions that we put inside the segments, and in this case, it's a financial function. And the way that we chose to model financial problems is in a special way because we realized that financial problems can be divided into two different parts. The first one is the financial model that is written here, and the second one is the financial function. It's basically the questions that we want to ask ourselves about the model. And I want you to notice this financial model is purely statistical model. It's a Gaussian model. It's basically a loss distribution portfolio of two assets. You can see I have two assets, and everything inside this model describes everything inside this function describes my model, and it has almost nothing to do with quantum computing. You don't really need to know quantum computing in order to write this model, except maybe for this line with the number of qubits, which represent the accuracy, the number of qubits that I allow my model to represent the Gaussian. So in this case, it's 2 qubits. It means 4 numbers are representing my Gaussian distribution. And the second part, it's the financial function. And because I told you that I'm doing risk analysis, the function, the question that I want to ask is basically, what is the value at risk for this distribution? And this is very flexible. I will show you in a minute how we can change it and how we can play with it. But in the meantime, I will generate the quantum circuit that solves this problem. Let's call it value at risk. And we can see that we got the Gaussian representation, and we got a quantum circuit that, first of all, is much more complicated than the circuits that we saw before. But the nice thing here is this circuit contains everything that you need in order to execute this model, this problem that we've just generated on a quantum computer. And you can ask me, okay, I don't really understand what you're showing me because this is a huge quantum circuit. I don't know anything about gate level representation. I only wanted to know what is the value at risk for this specific distribution. And I would say that you're right. So let's execute this quantum circuit. And in order to execute this quantum circuit, I need to open a new file. You can see that the suffix of this file is execute. All of these suffixes and files are relevant to our Classiq platforms. And in this execute file, we decide, we configure the hardware that we want to run to run our circuit on and to solve the question that we just asked. So you can see I have Azure Quantum, but let's just for sake of time, let's choose IBM, IBM Air Simulator. I choose the package name and Air Simulator, number of shots. And because this is a risk analysis, problem, we use amplitude estimation, and amplitude estimation is the quantum analog to the classical Monte Carlo simulation problem. So I want to solve this problem using amplitude estimation. I need to define the amplitude estimation properties. This is the confidence level, the error that I allow this algorithm to have, and this particular property, the value at risk, we chose to solve using a binary search method. So I want my tail to be 0.05%. And now I go to the command line of this code. I run execute quantum circuit. I choose the circuit that we just generated. It saves under var. Open it. Let's call it solution 1. And we got the solution to this circuit. To what is the value at risk for the model that we created. Now, you need to trust me on this number 2 here. I ran the numerical simulation, and the answer is very close to 2. But you need to remember that our world is now discretized, it's not continuous, so we can get the correct answer. And moreover, if you remember, I asked that the percentile will be 0.05, but I go 0.04, and this is because, again, this number corresponds to the value of 2 on the distribution. Okay, so I want to go back for a second to the financial model, and I want to show you that I didn't finish my risk analysis now, because the next property that I want to calculate now, it's not the value at risk, it's the condition value at risk, or as also known for the expected shortfall. And if you think about it, the expected shortfall, it's the expectation value of the tail of this distribution. So I want my model to calculate the tail distribution. So I'll give it the tail probability. And I designed it to be 0.05, but when we generated the circuit for the value at risk, I saw that I got 0.04. So this is the correct number that I need to insert here, the probability. And now again, I generate a quantum circuit. Let's call it CVAR, conditional value at risk. And voila, we got another quantum circuit that was generated really quickly. And this circuit contains in it everything that you need in order to solve this model. Now, the question that you asked on this particular model can verify from option pricing to moments that you want to calculate. It can be the second moment, the fourth moment. You can change the model that you're running, but I think that my main message from this part is that you don't have to be a quantum expert in order to solve some financial problems on a quantum computer. And this is due to the fact that our platform makes it accessible to you. Okay, I think we're ready for the last example, and this example is, as Amir said, is generating some complex oracles for a Grover search algorithm. And I hope some of you are more familiar with the Grover operator. Again, you can see that the structure of our model is the same. We have the number of qubits that we allow our circuit. We choose here the function. Now it's a Grover operator, and the parameters that the Grover operator is receiving is the oracle. And the nice thing here is that we allow you to insert a very complicated expression, very complicated arithmetical expression inside this oracle. So the expression that I chose to show you, it's a little bit more simple. It's A plus 5 XOR B modulo 8 equals 2. And you see it's an expression with 2 parameters. I need to define this parameter size. The size is in bits. How much do I how big do I allow these parameters to be? So A, I want it to be 3 bits, and B will be 1 bit. And I have the method, and this method is basically the uncomputation strategy that we use in order to build this arithmetical expression, because arithmetical expression have many ways that they can be inserted into that can be generated inside the circuit. So this method allows you some kind of flexibility in the way that you get in the way that you implement this arithmetical expression. And you can find the sweet spot. This flexibility comes in hand when you need to find the sweet spot between the depth of your circuit and the number of qubits that you are using. So let's generate the circuit. Let's call it Grover. And we see that we got here a little bit more complicated circuit. Here we wrap the building blocks of the arithmetical expression in the oracle, so it will be more readable and more understandable. And you can see we have here the plus, we have the XOR, we have the equality and the uncomputation part. And for those of you who are familiar a little bit with Grover algorithm, after the oracle, we have some kind of state operation or the unitary that we're acting on, and we have the diffuser operator and the dagger of this unitary. And basically, this circuit is ready to be executed as a Grover algorithm. And let's see what will be the result. We want to find A and B. Grover is an amplitude amplification problem. Let's choose 3 iterations. And in the meanwhile, you can try to think what will be the answer of A and B. Let's execute this file. Let's choose Grover. Okay, we got A equals 6 and B equals 1. Let's see if that's the correct answer. 6 plus 5, it's 11. So 1, it's 10. Modulo 8, it's 2. We got the correct answer, which is nice. Anyway, you can insert any kind of arithmetic expression that you wish. It can be with much more parameters. You can change the parameter size and the operators that you're acting inside the expression, and change the method. And you have a lot of flexibility to create your own circuits and algorithms. And I think that wraps up my demonstration. And Yuval, back to you.
Thank you very much, Lior. So just recapping what we saw 3 examples: a state preparation, including changing the constraints, a Monte Carlo simulation, and the generation of a custom oracle with arithmetic functions. These are all done using the Classiq platform that provides, one, the ability to define a high-level functional model and the constraints that the designer cares about, the ability to automatically generate a quantum circuit for the backend of your choice, and we saw a Q-sharp and Cassim, and a part that we haven't seen today, the ability to deeply analyze these circuits. Now, let's take some questions as we wrap up. One question for you, Amir, that came in. We showed here a couple of functions that exist in the platform, but what happens if I want to define my own function? Will I be able to extend the platform to include that function?
Yeah, that's a great question. So first answer is yes, you can. You can define your own functions and incorporate them within the model. But it's even stronger than that, because once you comply with the interface we require for defining new functions, you get also the many strengths of the synthesis engine, such as being able to reuse your auxiliary qubits, or with many different flexible ways to design the circuit, find the optimal one or optimize for a specific hardware. So really, it becomes much stronger than just being able to put in your own function.
Perfect. And another question that came in from the audience: could you please explain how to test and verify the quantum circuit that does give the correct result, both now and into the future, when we use more qubits and they're impossible to simulate on classical computers?
Right. Yeah, that's the part we were missing on the demonstration. So, of course, it's a hard problem. It's a hard problem to verify and to check these things. It is similar to classical verification problems. It's hard to find that the logic you're trying to have a billion-chip computer to do is actually functionally correct. So we're using similar methods within our platform in order for the user to check and also to automatically find bugs and insights on your quantum circuit.
Very good. And I think that's all the time we have today. We allocated 30 minutes. We'll respond to additional questions by email. And you can also reach us after the webinar, hello@classiq.io, or visit our website at www.classiq.io. Thank you, Lior. Thank you, Amir. And thank you for everyone that joined us.
Bye-bye.
Thank you.